Hey, welcome back to your favorite Calc 2 class, you guys. Just a little bit of background on area and arc length and polar coordinates. Um, the development for this comes from a sector of a circle. You know, the area of a sector of a circle is 1/2 r squared theta. And if you run uh, the iterative process on this, right, we split it up into all these small segments, and then we run the limit as n goes to infinity. In other words, the number of those sectors goes to infinity, or delta x, the width of those, if you will, goes to infinity, right? The iterative process. Then we're going to end up with our area in polar coordinates formula right here. Okay. Again, just running that limiting process there. I think it's worth your while to look at this polar sweep animation. So here's the animation of that with a polar sweep, you guys. I think this is gone, maybe. There we go. If you click on that link, it'll also give you the audio. But you notice as we go with our theta here, we trace the theta out, and it goes out our distance, right? Starting with theta being 0, and it starts to just plot all these points. And in this case, you get this rose curve with 4 petals, right? So that's kind of a nice sweeping out of theta as you progress, and then it does the entire rose curve. There's another one here with r being 3 sine of 3 theta, and so that would be another rose curve, symmetric about the x-axis. You can see as theta, as you throw in thetas and then increase with the theta progresses, it starts sweeping that out. So I think that's nice. I can't draw that, so get that picture kind of in your brain, and let's do some by hand. Here's one more where you've got a special curve here as well. Here's one with an inner loop, a rose curve with an inner loop. All right, so now we're going to go ahead and find the area of a swept out. In this case, we've got a rose curve, but we're just going to find the area of one petal of that. I want to kind of walk you through sketching this if you did not have the graph. The first thing I would do is I would sketch it in Cartesian. Coordinates first. So if you're thinking about this r equaling 3 cosine 3 theta, you know, your period on this would be 2 pi over that 3, right? And so some nice key points, if you were throwing in thetas and r's here, would be to go up by 1/4 of that, right? Split that into fourths. So in other words, pi 6, you want to go up by pi 6. So if you started at 0 and then you went up pi 6, and then pi 6 plus another pi 6 is 2 pi 6 or pi thirds. 2 pi 6 plus another pi 6 is 3 pi 6 or pi halves. 3 pi 6 plus another pi 6 is 4 pi 6 or 2 pi thirds, right? And this will give you one period of this. So if I go ahead and hey, let me erase some of this here for a minute. If I graph this now, here's my theta as the horizontal axis, r being my vertical axis. And now let's throw in theta being 0, right? So I throw in 3 cosine 3 times 0. I know the cosine of 0 is 1, so I get 3, right? So I get 0, 3. I throw in pi 6. So 3 times pi 6 is 3 pi 6 or pi halves. I know the cosine of pi halves is 0. 0 times that 3 in front is 0. And then I plug in pi thirds. I plug in the pi halves. I plug in the 2 pi thirds. And so I got 0, 3. I got pi 6, 0, pi thirds, -3, I have 0 and 2 pi thirds. I got 3. And of course, if I want to plug in, like maybe to the left, go down a pi 6 from 0, I could plug that in as well. And I would get 0 on that. So here's our initial 1 period of that. And of course, I did take it over to this one as well, but keeps going, and so on. So what I'm trying to show you here, now let's make the connection to the visual. Let's take this 0, 3 first. If r is 3 and theta is 0, right? R theta. So I'm right here. I have not moved, but I go out 1, 2, 3. There's that point. Oops, 1. That's terrible. 2, 3. Not even on there. 1, 2, 3. There it is, right there. All right. So there's our first point, or one of the points on this. Right. In fact, let's do that negative pi 6 right here, here, and here. I'm going to do those 3 points right there. So if I have a negative pi 6 angle, right? Negative pi 6 is my angle. My r is 0. So I don't move. So I'm right there at the origin, right? So it's starting there. And then if I like plugged in, let's say negative pi 12 or something, I get something over here. So it's moving this way. And then I'm going to get to this pi 6, r being 0. If I draw the pi 6, right, there's a rotation of pi 6, but it's also right there, r being 0, right? I don't go out anywhere. And so it's coming back around until it hits right back there. So that's one pedal from negative pi 6 to pi 6 is that first pedal. Are you with me on that? So that's what I want to do, is find the area of that. Area of one pedal. So I go ahead and I use that area formula that comes from that limiting process, from theta being alpha to beta. Okay? And we're just going to plug it in. So we got 1/2. My r here is 3 cosine of 3 theta. That's being squared. And I'm going to do one pedal. So I just want to go from negative pi 6 to pi 6. And so let's just work this out. I got 1/2 9 cosine squared 3 theta 2 theta negative pi 6 pi 6. Now remember, I'm going to have to use my power reducing. So cosine squared of u, if you look on your trig cheat sheet, that's 1 plus cosine of 2u all over 2. So that's what I'm going to do with that right there. So in other words, cosine squared of 3 theta would be 1 plus cosine of 2 times 3 theta all over 2. So we got 9/4 1 plus cosine 6 theta d theta. So that's the integral of 1 plus I'm going to let u be that 6 theta So I need a 6 and a 1/6. So I got 9/4, so I got theta plus, let's see, both those go into 3, plus 3/8. Integral cosine of u is just the sine of u, so sine of 6 theta. And then this is from negative pi 6 to pi 6. So we got 9/4 pi 6 plus 3/8 sine 6 times pi 6 minus 9/4 pi 6. I got plus that 3/8, that's the sine of pi, so that's 0, minus negative 3 pi 8. That's 3/8, that's the sine of negative pi, so that's 0. So we got 3 pi 8 plus 0, distribute that plus 3 pi 8, and then minus 0. So area of one petal would be 6 pi 8 or 3 pi 4ths. I do think it's of note here at this bottom here. If you were to find the area of all three, you just multiply this by 3. You don't want to integrate between 0 and 2 pi because that's tracing it out twice. That would be tracing it out twice, actually, when you go from 0 to 2 pi. Because you're actually doing it from negative pi 6 to 5 pi 6. It's also the same thing. It's a distance of 2 pi. From negative pi 6 and finishing it out 5 pi 6. You've done it twice. So you would actually want to do just half that distance if you want all 3 petals. So it's a little tricky on that. So be very careful about that. This is a great problem to pause the video and go ahead and try it. But I would go ahead, when you're checking yourself, go ahead and sketch the Cartesian coordinates here. You notice your period here is 2 pi over that 2. Okay? So your period is pi. So you want to cut that in fourths. So if you're plotting some points, theta's in r, you could start at 0 and then go up pi fourths. Pi fourths plus pi fourths is 2 pi fourths or pi halves. 2 pi fourths plus pi fourths, 3 pi fourths. 3 pi fourths plus pi fourths is 4 pi fourths. All right? And then you throw them in one by one. You throw 0 in for theta. R equals cosine of 2 times 0. Well, we know the cosine of 0 is 1. So we got 0, 1. Throw the pi fourths in, you get 0. Throw the pi halves in, you get negative 1, 0, and 1. So I got 0, 1, pi fourths, pi halves, 3 pi fourths, and pi 0. And I'm also going to go back to this back pi force right here so that I have a R value of 0 as well that it goes through. That's going to help me out when I go ahead and graph this. So I am going to throw that in, that negative pi force comma 0. Now let's think about how does that transfer over. Well, let's think about these points. How about the R being 1 and 0, R and theta, right? And also think about on your handout, cosine of n theta, right? This is a rose curve. So I'm looking at line second to the bottom on my handout, rose curve. I've got a cosine n theta, so it's symmetric about the x-axis with 2n petals. 2n petals. Well, 2 times 2, because that n is 2, is 4. So I'll have 4 petals, symmetric, rose curve, symmetric, about the x-axis with 4 petals. So I'm going to make a note of that. Now let's graph this first one. If my theta is 0, so I'm this angle right there, but I don't, and then my r is 1, right? So my r is out 1. Let's do the next one. My r is 1, or I'm sorry, my r is 0. My theta is pi 4, so if I rotate pi 4ths, but I don't go anywhere, my r is right there. Okay, there's another one. So it's coming around. My rose curve is going to be coming around to there, right? That's what I have so far. Now the question is, I know the symmetric about the x-axis, so I'm going to use that negative pi 4ths 0. Negative pi 4ths, but it's 0, so it starts right there and not going out any distance. Now I could put in some other ones to kind of help me to draw this out between negative pi 4ths and 0, like negative pi 8ths, for example, would be a good one to throw in. And it, you know, if I had negative pi 8ths, my r is, it's out that distance. I don't know, whatever that is, but it's on that rose curve, right? And I could keep going with this, but you're just going to see this thing with all 4 petals. All right, what we're concerned with is, can we find the area of one of them? Can I find the area of one of these petals? So we're going to go from that negative pi 4ths to the pi 4ths, right? So we can find the area of one loop. So we got 1/2. We're going from negative pi 4ths to pi 4ths. Our r here is cosine of 2 theta. That's r has got to be squared though, d theta. Okay, so we got 1/2 cosine squared of 2 theta. Plus. So again, I'm going to use that power reducing. Cosine squared u is 1 plus cosine of 2u all over 2. And use u substitution. Oops, and I should have had a 1/4 here already. Make a note of that. I already have this 1/4. Remember, the 1/4 goes to both of those. I already had that already. So I've got 1/4, integrate that theta, plus I got a 16th now. Integration of cosine of u is just the sine of u, and our u here is 4 theta. We're going from negative pi 4ths to pi 4ths. So 1/4 times pi 4ths. 4 times pi fourths minus sine of pi is 0. So we got pi 16th plus pi 16th, 2 pi 16ths, which is pi 8ths. Another great problem, you guys, to pause the video on and go ahead and try it first. But let's go ahead and sketch this in Cartesian coordinates again with our thetas and our r's. You know, our period here is 2 pi over 2, so our period is pi. So I'm going to go ahead and start at 0, but I'm going to go up a fourth of pi, right? So I'm going to go up pi fourths. I have go up pi fourths each time into pi. That'll give us one period of this. And then I'm going to throw those in one by one. I'll get 0, 3, 0, -3, and 0. Again, this is theta, that's r. Pi fourths, pi halves, pi fourths, and pi. Now, if I look at the polar curve handout, I'm going to have a rose curve that's symmetric about the y-axis with 2 n petals, where our n here is 2. So I'll have, 2 times 2. I'll have 4 petals, and I'm going to be symmetric about the y-axis. 4 petals symmetric about the y-axis. Let's use some of these points. Let's start out 0, 0. So if I don't rotate anything, I'm still at 0. I'm right at the origin. So I have that dot right there at the middle. Now let's go and let's rotate pi fourths. If I rotate pi fourths, I'm out. So now I'm using this point, r comma pi fourths. That's my r, that's my theta. So I'm going to go out 1, 2, 3 right there, right? Oops, should give me that dot right there. And then if you notice, so I've used that one. If you notice at pi halves, so 90 degree, I'm back to 0. I'm back to that point right there again, right? So this will do one petal. You could plug in, like maybe you want to plug in a pi 6 as well if you want to, and you'd get a point on there. Oops. Get a point on it, and it's going to come around. You know, maybe you want to do pi thirds as well, and you get another point. So you're going to see this thing coming around and showing you that one petal as you get back to an r of 0. Or I'm sorry, pi thirds is up here. Sorry about that. That would be up here. Coming around, coming around, coming around. There's your one petal. And you can keep tracing it out, and you'll see all 4 petals. Very tedious, obviously, doing this by hand. But we're going to use those 2 points from theta being 0 to theta being pi halves. That'll give us the area of one petal. Our r here is, let's see, it's 3 sine of 2 theta. That's being squared d theta from a theta being 0 to a theta of pi halves. So I got 9 sine squared 2 theta, so I'll have a 9 halves sine squared of 2 theta d theta, 0 pi halves. So we got 9 halves. I'm going to use that power reducing again. So I'll have 1 minus cosine of 2 times the 2 theta all over 2. 9/4 1 minus cosine 4 theta d theta. So I'm going to let my u be that 4 theta. So it'll be 4 d theta, which means I could offset it. 1/4. So we'll have 9/4 theta minus 9/16 integration of the cosines of sine from 0 to pi halves. So 9/4 pi halves, 16 sine 4 times pi halves, minus, let me come down here at the minus, now I'm throwing in the 0. So it looks like we got just 9/8 pi, area 1 pedal. All right, let's go ahead and find a region between a couple of curves now. This first one, notice it even tells us, hey, this is a circle, r equals 3 sine theta. You can look on your cheat sheet if you want to, and you can see that it's going to be centered on the y-axis. If you're not sure, let's just change it to polar. Let's go ahead and multiply both sides by r. And we got r squared, or x squared plus y squared equals 3r sine theta. So there's a y. So we got x squared plus y squared minus y equals 0. And I could go ahead and, equals 3y, I'm sorry. That's 3 times r sine theta. There we go. I would complete the square, negative 3 over 2 squared, so that's 9/4. I want to throw in a 9/4, so 9/4. That would help us to complete the square. So you just have a circle centered at 0, 3 halves with a radius, r squared is 9/4, with a radius of 3 halves. So now you can kind of draw that on your polar graph. Now you know what, let me do it like this. Circle centered at 0, 1.5. And then it's got a radius of 1.5. Yeah. Oh. Come on, now it won't draw a circle for me. I don't know. Anyways, move that over. I can't get the dang thing to work for me. This is my last one, I promise. I suck. Well, that's the best I'm going to get that circle, looks like. Oh, well. Me and tech do not get along all the time. So this is a... if I'm looking at my my cheat sheet, I've got a limosone, and it's a cardioid specifically. AIOID. So symmetric about the y-axis. If you're looking at that, I would probably still, like, you got to get a picture of this thing. Do some thetas and r's here. Your period here is 2 pi over 1, so my period's 2 pi, so I take a fourth of that, which is pi halves. So I start out as 0, go up pi halves, pi, 3 pi halves, 2 pi, and I throw those in one by one. Let's see, that'll give me 1. I'm also going to go back pi halves as well. So this is the sine of theta bumped up one. So that's just showing me or showing the midline there. Okay, come down to there. Anyways, all right. So I'm going to start out. Let me use this right there, that r being 0 and the negative pi halves. This is my r, this is my theta, right? So if I am negative pi halves, I'm right there at r being 0. There's 1 point. Let me do 0, so I rotate 0. My angle is 0, but I go out 1. Let me do the next one, r being 2, and I rotate pi halves. So I'm right here. Rotate pi halves. I go out a distance of r being 2. Let me rotate 3 pi halves, and I'm back to 0. That's right there. Oops, 3 pi halves. And 2 pi back to 1. And I could throw some others in, but I'm cheating and looking at my limits on the cardioid on there. So again, I'm looking at my handout. I have a cardioid, symmetric about the y-axis. Cardioid is where you've got r equaling a plus or minus b sine theta. Here we have 1 plus sine theta. So my a and b is 1. So my a over b is 1. That's how I know it's a cardioid. And I could plug in a few more points and see, like, between, for example, the r being 0 and negative pi halves 1 to there. And I get a few of these. It's going to come around. It's going to hit. It's also going to hit right here. This is at theta being pi 1. I didn't plot that point. I should have. And that's going to hit right there. So it's like coming around like this kind of thing. Okay. Now what we want is it's asking for the area that's inside the circle and outside the cardioid. So let me do that in red. That would be this right there in red. Okay. So we need to know, first of all, where do these things hit? Here and here. Where's their intersection? And then what I'm going to have to do is I'm going to have to take the area of the circle inside that, from that region. Here, let me trace it. So area of the circle would be green from this theta to that. And then I'm going to go and subtract out the area of the cardioid piece. If I did that in black, that's the piece. Oops. Do that. Subtract out the black piece, and that would leave me with the red up there, top. Okay. So that's kind of the plan, but we've got to find the intersection first. So where do they hit? Where does this R equal that R? So I subtract sine of theta on both sides, so I get 2 sine of theta. Where's the sine of theta equal a half? And I say that's at pi 6 and 5 pi 6. So this is pi 6 right there. This is 5 pi 6. Okay. And the plan is I'm going to do area of the circle piece, subtract out area area of the cardioid piece. Going from pi 6, 5 pi 6. My R is 3 sine of theta. So that'll be squared. And then minus cardioid is 1 plus sine theta. So 9 halves sine squared d theta. Minus a half. And I'm going to expand 1 plus sine theta times another 1 plus sine theta. Foil that out. 1 plus. So that'd be 2 sine theta plus sine squared theta d theta. Use that power reducing. I use the power reducing on that sine squared as well. And 9/4 minus 2 theta. Do substitution there. I split that up, right? So that gets all from pi 6 to 5 pi 6. This will end up being this whole thing. So plug in the 5 pi 6 to everybody, plug in minus, subtract pi 6. I am running out of room. I do have the answer here. This does end up being pi. All right, we've got a circle again. It tells us this r equals -6 cosine theta. If I multiply both sides by r, I get r squared equals -6 r cosine theta. So x squared plus y squared equals -6x. So x squared plus 6x equals y, or I'm sorry, plus y squared equals 0. Go ahead and complete the square. So 6 over 2 squared is 9. And you've got x plus 3, 20 squared plus y squared equals 9. So this is a circle centered at -3, 0, the radius of 3. Right? So what you're wanting to graph here. Anyways, I couldn't get quite to hit at those points, but that's about as close as I can get here. Now this one, we've got this 2 minus 2 cosine theta, right? So we've got another limison with r being a plus or minus b cosine theta. So this is symmetric about the x axis, and my a and b are 2, so a over b equals 1, so that's why it's the cardioid. So it's going to have that little dip into a piece of it there. So let's kind of get a picture of what this thing will look like. My period, actually let me give myself a little room and erase this for a minute. 2 pi over 1. I take 1/4 of that, so I'm going to throw in 2 pi 4s or pi halves. I'll go up by pi halves, pi, 3 pi halves, 2 pi, and so on. I'm going to throw those in, so that'll be 0, pi halves 2, 4, 2, and a 0. If I was graphing that, I'd have pi halves. Let's see, pi halves 2 pi comma 4. Pi comma 4, 3 pi halves 2, and 2 pi 0. Kind of coming like this here. All right, our midline's right there. All right, let's take a few of these points. Let's take a look at this r. If r is 0, my theta 0 and r 0, so we're right there. Now let's go to the next one. If I rotate pi halves and I go out a distance of 2, I'd be right there. Let's go to that pi 4. Or rotate pi. 1, 2, 3, 4. I'd be right there. Let's do that next one. R is 2, 3 pi halves, so I'm like right here. And, maybe I want to do another one like maybe 2 pi thirds. 2 pi thirds is, 120 degrees. If I plugged in 2 pi thirds, you'd get, so let me plug 2 pi thirds in, and you'd end up with 3 there. So you go out 1, 2, 3, so you end up with like right there. And anyways, you could get a few more on this, but you're coming around. This is theta beams here. that right there. Okay. Now we need to know where do they intersect. That black point. Oops. And this black point. I didn't draw this the greatest. Look at it on decimals if you want to. So where does this R equal this R? So let me add 2 cosine of theta to both sides. I add negative 4 cosine theta equals 2. Where's cosine theta equal negative a half? So 2 pi thirds and 4 pi thirds. So this is right here. That's that point. Theta being 2 pi thirds. And this is the point theta being 4 pi thirds. And so what we'll do to find the area between the circles, and between the regions bounded by them. And if you could kind of picture, this is rotating around, right? And it's finding that area in that area, right? As theta rotates around. It's fun. So that's kind of your visual with my very poor. Oops, too much. So now if I could try to kind of draw this, I'm going to take, I'm looking at my circle. It has this point. When theta is pi halves, my R is 0. And it goes around until my theta is 2 pi thirds right there where they both meet. So I'm going to go and find the area between the circle from pi halves to 2 pi thirds. Okay. So I'm going to set that up first. Let me see if I can't. So this is area of the circle from, so 1/2 r squared, which is negative 6. This is my circle. I'm going from theta being pi halves to 2 pi thirds. Okay. And then I'm going to add in the area on this cardioid between that 2 pi thirds, and right here, if I rotate pi, if I rotate just pi amount, I'm out 4, right? So if I go to pi of the cardioid's 2 minus 2 cosine theta squared, so 1/2 r squared theta. And that'll do, let me come up here, that'll do this blue area. Now I know it's double that because I need this blue and I need that red as well, right? So this is actually only half of it. And so what I'm going to do is I'm just going to double it. So let me go 2 times this whole thing. And we continue on here, we distribute that 2 through, and we'll end up with, this will be 36 cosine squared theta. And go ahead and expand that out, so that'll be 4 minus 4 cosine theta plus 4 cosine squared theta d theta. I'm going to use that power reducing for cosine squares. So that 1 plus cosine 2. I just realized I got 4 minus 4 cosine minus 4 cosine. That's an 8 cosine right there. Sorry about that. Now I've got a cosine squared, so another power reducing on this. I'm going to go ahead and let u be 2 theta on that. And same thing over here, I'm going to let u be 2 theta on that. So I get 18. Pi halves, so 2 pi thirds. And then pi, I would combine those right there. I'm kind of running out of room here, but this will end up, if you plug those in, this will all end up being 5 pi. All right, let's do another one here before we move on with a little commentary. Let's start out with our Cartesian graph with theta and r. Notice my period here is 2 pi over 1, so I'm going to go up by a fourth of that 2 pi. So I'm going to go up by pi halves amount from 0. So up pi halves, pi, 3 pi halves, 2 pi. And we could continue on if you wanted to, but let's go ahead and graph this with our theta and r. Plug the 0 in, put the pi halves in, put pi in, 3 pi halves, plug the 2 pi in. Let me move that down a little bit. Zero, 1, pi halves, -1, pi 1, 3 pi halves, 3, 2 pi 1. Now this is a sine curve flipped over, it's stretched out, right? By 2, and then up 1. So your midline is right there on that. Let's go to our polar graph now. Now if I'm looking at this, oops. This ends up being a limicone, I'm sorry. So a plus or minus b sine of theta if you're looking at your handout. And notice the a over b, the a is 1, the b is 2, is less than 1. And so it's a limicone with an inner loop. So I'm going to write that. This is a limicone with an inner loop because that A over B less than 1. Okay. Let's go ahead and do a few points here, like R, if R is 1, theta is 0, here's R, theta, I'm out 1, so if I, theta being 0, I'm not rotating, but I'm out here at 1. Let's do pi halves, negative 1. So pi halves, and then opposite, negative 1, I'm right there. We could do, and you could do some between there, like maybe you want to throw in pi sixths, and you get 0. So R 0 when theta is pi 6, right? So theta being pi 6, you're right there. All right, so you're kind of coming around. Oops. And you have an inner loop. And I don't mind if you use decimals on this. You're going to hit here. It'd be nice to hit. You could also do like maybe 5 pi 6 and some other points here, but you're going to come around, hit. Let me throw on pi 1. That'd be that point right there. So I rotate pi, go out distance 1. Hit right there. Let's do 3 pi halves, 3. Rotate 3 pi halves and go out a distance of 3 for that point. Oops, that's not very good. Like I said, not a bad idea on this one here. Throw on, whoops, decimals. You throw on R equals 1 minus 2 sine theta. And you can see that with an inner loop right there, right? Oops. Technology assistance on this one. Now what we're doing is we're trying to find the area of the region lying between the inner and the outer loops. So let me do this in, let me do that inner loop there in red, okay? And for this inner region, right, the inner loop would go, let me put on this point here, is 0 pi 6. And then when does it hit it again, right? When does R equal 1 minus 2 sine theta hit that again? You know, because it's coming around, all right? So I know at pi 6 I have an R that's 0. Let's find where else is my R 0 after pi 6, right? When does 0 for R 1 minus 2 sine theta? In other words, when does the sine of theta equal a half? Well, we know it hits it at pi 6, and then if I look at my unit circle, 5 pi 6 is your other one, right? So it comes around again at 5 pi 6 and hits at 0 again. So it comes around, and when R is 0, when theta is 5 pi 6. 5 pi 6, so 5 pi 6 is kind of like that rotation, but the R is 0 again, right? So that's the inner loop. So if I find the area of the inner loop, right? Now I know I'm finding the area between them, but what I'm going to do is I'm going to find the whole area in green, whoops, And I'm going to subtract out the area in red, and then I'll be left with what I want between them. Okay, so let's do the inner loop in red first, the area of the inner loop. So part C or whatever I'm doing here, area of the inner loop, I'll call it A1. So I've got 1/2 r squared d theta from alpha to beta. So this would be 1/2 from pi 6 to 5 pi 6 of 1 minus 2 sine of theta squared d theta. So 1/2 minus 4 sine theta is 4 sine squared theta. Half minus 2 sine theta plus 2 minus cosine 2 theta, 2 theta. I got theta minus 2. And I would combine those two. Pi 6 to 5 pi 6. And so this area, this inner loop, will end up being pi minus 3 root 3 all over 2. All right, now let's do the area of the outer loop, right? And so for that one, I want to go around more than 5 pi 6. So I'm thinking, so I'm starting out, let me do it in orange right here at pi 6. Oops. Let me try that again. Right there in orange. It's coming around, it's hitting it at 5 pi 6, but I got to keep going, right? I got to keep going, keep going, keep going, keep going, keep going, keep going until I hit it again right there. So when would that hit that again? Well, when I have that angle again, I go around to that angle pi 6 plus 2 pi, so at 13 pi 6, I'm back at 0. R theta. So for this outer loop, I want to go from pi 6 to 13 pi 6. And that would give me the area there. Oops, don't erase it. So area of the outer loop, call it A2, 1/2 from pi 6 to 13 pi 6 minus 2 sine theta squared d theta. And so this is the same integral, right? So we'll end up with this. And so this area 2 would be 3 pi. So lastly, the area between the two loops would be area 2 minus area 1. So that would be 3 pi minus pi. 3 pi minus pi is a 2 pi. There's our area between them. Or about 8.881 if you punch that in. Just note, you guys, with intersections, because a point may be represented in different ways, you got to be careful in determining the intersection. Okay, so for example, this one is showing here the limacon and the circle, right? And you can see that if you were to solve where you put these two together, you know, where does this R equal that R? And if you solve that, right, you get the pi halves, you get the 3 pi halves, right? So it's giving you that one, and it's giving you that one. But notice, you're missing one intersection on this, right? There is a third one. And so, you know, there's a reason for this. So, in other words, sketch it out can be helpful, right? So you don't miss a third point. And the reason that doesn't show up is because it doesn't occur with the same coordinates in the two graphs, right? You'd have to let R be -1 in order to find this third point of intersection. Okay, so you got to be a little careful about that. And finally, I like this commentary here. You know, you can compare the problem of finding points of intersection of two polar graphs with that of finding collision points of satellites. Right? Satellites will not collide as long as they reach the point of intersection at different times. Right? Collisions will only occur when you have simultaneous points, when they're reached at the same time or theta value. Right? That's the only time that the satellites would collide. And I'm going to end it right here and start another video for the next part.